Great, so thank you very much for being here today. So today we'll be talking about haptics for human-centered robotics, and especially focusing on the great potential of cutaneous haptic feedback. Now, before going into the details of this very exciting topic, let me first very briefly introduce myself. So my research path started back in 2012 as a PhD student at the University of Siena. After that, I moved to Genova to become a postdoctoral researcher at the Italian Institute of Technology. And then finally, at the end of 2016, I moved to Rennes, France, to become a permanent researcher of the CNRS. Now, throughout all these years, my work revolved always around haptics for robotics, from the earlier work on robotic telemanipulation to the more recent results in area robotics, virtual reality, and micro-robotics. I am part of the CNRS, which is the largest fundamental science agency in Rennes and in France and Europe, with over 28,000 researchers that address all fields of science. And I'm based in Rennes, which is a very beautiful city in the northwest part of the country. And there I'm part of a research laboratory called IRISA, in which our team, Rainbow, focuses on advancing the state of the art around sensor-based robots that navigate and collaborate in complex environments together with humans. My research revolves around haptic science and technology. Now, in analogy with optics and acoustics, haptics is the science that studies and explores the sense of touch. In the same way as graphics and audio target our sight and hearing, haptic technology targets our somatosensory system, the sense of touch, to convey rich information to a human user, for example, the feeling of touching virtual and remote objects, or for providing navigational cues. Haptic sensations are delivered through a combination of cutaneous and kinesthetic sensations. Cutaneous sensations are detected by receptors in the skin, enabling users to recognize the local properties of objects, such as the local shape, temperature, and texture. On the other hand, kinesthetic sensations
clear so that if visitors want to get this large food,
come from the afferent information.
And it's kind of a known
I feel that
track versus the demos of the student robotic showcase is normally a shorter period of time, a smaller amount of space. I
maybe connected to another room.
Co-chair, so there was
without
a
haptic,
process which I think something as well. If anyone's interested,
we hear it, but we cannot
submit information. They're no told how much space they would have, so
that is great. Thank you very much for this. So what I was saying, so on one side we have cutaneous, so local sensation. On the other hand, kinesthetic sensations come from the afferent information originating in the skin, muscles, and joints, and provide information about the position and velocity of neighboring parts of the body, as well as the applied forces and torques. So when we talk about haptic technologies, we refer to our capability of devising artificial systems capable of sensing and transmitting all those pieces of information that we humans experience when physically interacting with the surrounding environment. Grounded kinesthetic haptic interfaces have been widely used in robotics. They provide compelling force feedback via desktop device actuating a moving end effector, often shaped as a handle, a pen, or a sphere. You can try some of these devices at the exhibition hall. These devices can be seen as force-reflecting joysticks in which the same end effector is used to control a remote or virtual agent, as well as provide force feedback about the interactions of that agent with the target environment. Grounded kinesthetic haptic interfaces have been mostly used for high-end applications, including medical robotics, space telemanipulation, and in the nuclear industry, thanks to their great capability of providing compelling sensations about the shape, weight, and stiffness of virtual and remote objects. On the other hand, cutaneous haptic devices offer localized feedback, focuses on tactile sensations such as texture, friction, and local shape, often delivered directly to the skin, often through moving pins and plates. Now, what makes Cutaneous Haptics devices particularly appealing is their great potential for high wearability, portability, and cost effectiveness, which can potentially revolutionizing the way we interact with everyday technology, from gaming to in-home rehabilitation, especially with respect, especially if compared with standard kinesthetic devices. Indeed, research in haptics very often stems from needs arising from very diverse applications, looking for a better way to interact with their human users. And from these needs and requirements, we devise new haptic interfaces, control techniques, and interaction algorithms with the objective of enriching the way human users and artificial systems collaborate and communicate together through the sense of touch. Today, I will focus on the use of cutaneous haptics for robotic telemanipulation and immersive environments. Indeed, the grounded kinesthetic haptic interfaces have been widely used in robotic telemanipulation, being actually one of the very first fields in which we have used these devices. However, despite the great expected benefits nowadays, commercially available telerobotic systems provide very limited haptic feedback. Why is that? Well, this is due to a few different reasons, including the negative effect that kinesthetic feedback might have on the stability and safety of the teleoperation loop, as well as on the complexity and cost of kinesthetic devices. Indeed, it is known that outputting grounded forces during the teleoperation might lead to undesired oscillations at both sides of the system, which interfere with the operation and might even be dangerous. Of course, stability control techniques can be employed to guarantee safety at all times, but at the cost of reduced transparency and realism. Moreover, the complexity and cost of kinesthetic devices very often limit the potential for multi-point interaction. So, for all these reasons, in the past few years, we have witnessed a growing interest around cutaneous haptic solutions. Indeed, as the feedback provided is local to the skin and therefore decoupled from the end effector used to control the motion of my remote robot, providing cutaneous haptic feedback in teleoperation does not affect the stability and safety of the teleoperation loop, leaving it as stable as it would be if no cutaneous feedback was applied. This feature is, of course, especially relevant and promising for all those fields of applications in which the safety of the system is of paramount importance, for example, in medical robotics. Very well, now almost 10 years ago, we published one of the very first papers showing the viability of using cutaneous haptics in robotic telemanipulation. We used two cutaneous fingertip devices worn at the thumb and index fingers to control the motion of a remote robotic hand, as well as provide force feedback about the interactions of the robotic hand with the target environment. This during a peginal task using a telerobotic arm. Each cutaneous device was composed of 3 motors, moving a rigid platform directly on the fingertip of the user, as you can see here. This feedback enabled us to provide a one-to-one localized cutaneous information about the contact forces exerted by the fingers of the robotic hand holding the peg. The results of this peginal task showed that cutaneous-only feedback can provide rich and effective information about the forces exerted at the remote side of the system, as expected, without needing any additional stability control, even in the presence of communication delays and stiff contacts. However, Results also showed that cutaneous feedback led to higher forces applied onto the peg with respect to using standard kinesthetic feedback via grounded kinesthetic interfaces. But this is quite expected, right? Because of course, kinesthetic feedback literally blocks the motion of the user's finger, preventing them from applying too much force even if they want to. On the other hand, cutaneous feedback is applied locally to the user's fingertip, leaving the user free to move the fingers however they want. So now, this freedom of motion, therefore freedom of choice for the user, can be seen as a positive feature or a negative drawback, depending on the nature of the task. After this first promising work, we applied the same approach to robot-assisted medical palpation. The same cutaneous device, augmented with a vibrotactile motor placed right below the platform moving onto the fingertip, was attached to the console of a Da Vinci surgical robot. It provides contact deformation and vibratory sensations about the interaction sensed by a biomimetic sensor attached to one of the Da Vinci surgical tools. This during the palpation of a soft tissue phantom that represented a heart model. A model-free data-driven algorithm mapped the sensations registered by the biomimetic sensor at the patient's side into inputs for the 4 motors of our cutaneous device, enabling the operator to appreciate the compliance and local shape of the soft tissue phantom during the palpation, so as to be able to locate a calcified artery model that was hidden inside the phantom. Results showed that providing cutaneous haptic feedback significantly improved the performance of the palpation task with respect to providing standard visual feedback only, leading to lower forces applied onto the soft tissue phantom, as well as to lower errors in locating the presence of the calcified artery model. Overall, at a first glance, it seemed that contact deformation feedback provided by the moving platform onto the fingertip of the user was more informative, was more important than vibratory feedback provided by the vibrotactile motor to locate the presence of the calcified artery model. However, by looking at the data a bit more, we realized that this very much depended on how users explored the surface of the soft tissue phantom. For example, for users that were dragging the biomimetic sensor across the surface of the soft tissue phantom, vibratory sensations were more important than contact deformation feedback. These very nice results showed a bit the multifaceted nature of our sense of touch, as well as highlights how not trivial it is to choose which type of feedback is best to convey according to the type of task and system. Very well, now, until now, we have seen that cutaneous haptic feedback can be used to render some physical property of a remote environment. And we have achieved similar successful results also in robot-assisted needle insertion and robotic cutting. However, of course, haptic feedback can also be used to provide abstract information during the teleoperation, for example, navigational cues. In this respect, a few years ago, we used haptic guidance to help a human user pick up and place a series of very diverse objects using a telerobotic arm. Kinesthetic feedback provided kinesthetic guidance to guide the user towards a set of good grasping poses defined onto the different considered objects. At the same time, cutaneous haptic feedback delivered via wearable bracelet provided additional information regarding the vicinity of possibly dangerous configurations of the robot. So as you can see, in a certain sense, the use of cutaneous haptics paved the way to providing multiple pieces of information at once, leveraging the large size of our skin. Results of the pick-and-place task showed that the proposed mixed cutaneous kinesthetic approach outperformed standard human-in-the-loop teleoperation. Very well. Now, in the same way as cutaneous haptic feedback can improve interactions with remote environments, it can also benefit immersive applications. Indeed, nowadays, the recent popularity of augmented and virtual reality headsets is bringing interaction with virtual content in our everyday life. However, also here, technologies for providing haptic sensations are mostly lacking. Of course, grounded kinesthetic interfaces can be used for this purpose. However, their reduced workspace and significant cost very much limit their applicability to high-end applications such as medical and industrial training. So also here, cutaneous haptics provide a very interesting solution, especially for everyday immersive applications, such as gaming, retail, and automotive. Of course, it very much depends on the specific needs of the task and scenario at hand, and it is important to highlight that we can combine cutaneous and kinesthetic technologies to achieve intermediate designs. For example, a few years ago, we designed a very nice wearable encounter type haptic interface. It is composed of a motor placed on the side of the hand that moves a tangible sphere in and out of contact with the user's palm. The sphere is also equipped with a series of electrodes, enabling the system to detect when the user grasps the tangible sphere so that we can animate the virtual end avatar in the virtual environment accordingly. The sphere can also be equipped with vibrotactile motors so that we can provide additional impact and texture sensations. And we have used this device in quite a broad range of scenarios. For example, in this video here, you can see a human user playing fetch with a dog, picking up apples, and so on. It was quite fun. And in a later design, we also added a hand exoskeleton in order to be able to combine force feedback at the fingers with encounter type haptic sensations at the palm. Of course, we are working on cutaneous haptics in a much broader range of scenarios that I cannot all present today, but very briefly, for example, we are using innovative ultrasound mid-haptic technologies for providing contactless haptic sensations in virtual reality. We are using wearable cutaneous devices for providing situational awareness and guidance during human interaction with multi-drone systems, as well as during the steering of mobility assistive devices. And more recently, a couple of years ago, we started a large-scale collaborative European project whose objective is to devise haptic shared control techniques for steering multi-robot systems at the micro scale. Very well. Now, to conclude, I would like to direct your attention towards two take-home messages. So first of all, haptics is fundamental in our lives. Without the sense of touch, we'll be unable to carry out most of our daily activities, such as walking or manipulating objects. But not only that. For example, in these two pictures here, you can see a special room set up in a retirement home in Italy during the early COVID period, in which the elderly guests could physically, haptically interact with their loved ones in a safe manner. This because the sense of touch is pivotal for our interaction with each other and the surrounding environment. Despite all these, nowadays, technologies for providing haptic sensations are missing for most robotics and immersive applications. So it is fundamental to work to devise innovative and effective haptic interfaces and rendering techniques to fill in this gap for the broadest range of applications. Indeed, I see haptics as a fundamental enabling technology for empowering humans through robots. So mine is an encouragement for all of you to consider haptics as a meaningful tool to communicate between humans and robots. Nowadays in robotics, the potential of haptics is severely underexploited. The second message wants to highlight the complexity of our sense of touch. Nowadays, there exists no interface capable of wholly capturing the intricacy of our haptic sense. There exists no haptic interface able to provide a perfect representation of a virtual or remote environment. So, we need to seek for the best compromises. For each task and scenario, it is important to study which are the most salient pieces of haptic sensations to render, and then focus on those to develop haptic interfaces and rendering techniques well able to elicit that representative pieces of information. Indeed, more expensive and more complex haptic interfaces do not always mean a richer or a better interaction. The success story of Cutaneous Haptics shows us that indeed, in some cases, simple interfaces can lead to meaningful interaction. The simplicity and effectiveness of Cutaneous haptic devices can open to the use of haptics to a much broader range of scenarios, paving the way to simple yet effective haptic systems capable of revolutionizing the way we interact with all cyber-physical systems. To conclude, I would like to thank all the Rainbow Group in Rennes, all IRISA, as well as all the other colleagues with whom I have been working with in the past few years around these very interesting topics, as well as all our funding bodies that enabled us to create such a great research group. Thank you very much.